We had 2 sets of homework last night. It was worksheet number 12, questions 4 and 5. We also had some check and reflect questions on page 601. We're going to take a look at worksheet number 12 here first. Question number 4, you see the answer up on the board. Question number 5, I haven't put it up on the board because we're going to do that anyways, whether you think you need it gone over or not. Is there anybody that needs number 4 gone over? Number 4? Yep. Okay. Let's go over number 4 and number 5 then. 4 says, what's the kinetic energy in joules and electron volts of an alpha particle? I circled alpha particle here. Okay, you can see, even though sometimes when I'm doing an answer key, I don't show as much work as I should and whatever, I still circled alpha particle. Why did I do that? To draw attention to the fact that it's not an electron. We're so used to using electrons, we want to draw attention to other things, like an alpha particle. The mass is different, the charge is different, and we got to catch that. The alpha particle is moving through a magnetic field of strength 1.0 times 10 to the negative 1 Tesla and follows a circular path of radius 0.025 meters. In order to calculate kinetic energy, I mean, it's really fundamentally, it's straightforward. It's just putting it into play, putting it into practice. It sometimes gets a little bit trickier. We want to find kinetic energy. We know we always use 1/2 mv squared. We don't really have any other option. Okay, that's the formula for kinetic energy. But the problem here is we don't know what v is. We don't know what the speed is. So this is where we're going to start using what we learned over the last couple of days. Fc equals Fm. As this alpha particle goes through the magnetic field, it follows a circular path. And that circular path is caused by a magnetic force, which results in that centripetal force. We set those two forces equal to each other, and we end up with mv squared over r equals qvb. V's cancel. We get mv over r equals q times b. We end up solving for v. Take the r up by multiplying, the m down by dividing. V is equal to q b r over m. Remember what q is? You don't have to remember what q is. Check your data sheet. It says for an alpha particle, it's 2e. What's an e mean? The elementary charge, so it's 1.6 times 10 to the minus 19. The charge becomes 3.2 times 10 to the minus 19. We're given B, we're given R, and the mass is also on our data sheet. For an alpha particle, it's 6.65 times 10 to the minus 27 kilograms. We plug those numbers in, and for the speed, we end up getting 120,300.75 meters per second. In other words, 1.2 times 10 to the 5 meters per second. Is that a reasonable speed for a speed of an alpha particle? What do we say are typical speeds? Usually it's 10 to the 5-ish, 10 to the 6-ish. Okay, that's right in there. It's right in that ballpark. So there's no guarantees that I've done that correct, but the odds are pretty good that I've done it correct. We take that number, we plug it in over here. Again, we know the mass. It's on your data sheet. And we now know the speed. When we solve for kinetic energy, we end up getting 4.8 times 10 to the negative 17 joules. Now, we want that in electron volts. Let's do our conversion. We know that 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. Say we know that. We don't necessarily have to know that, because we can always look on our data sheet, right? It says 1 electron volt equals this. We're just kind of making it a fraction instead of an equality. 1 electron volt over 1.6 equals x electron volts over 4.8 times 10 to the minus 17. Okay, the 4.8 goes up by multiplying here, and we divide 4.8 by 1.6, and we end up getting, for x, 3.0 times 10 to the 2, or 300 electron volts. Good? Okay, I wouldn't say that was a trivial question by any means. It wasn't, I wouldn't say it was easy question by any means, but it's a question that we can get. Okay, with practice we can get it. Now, if you didn't get it last night, that's okay, because it's the first time that you would try a question like this, right? You know, as we see it done for us and we become better at this stuff, then here's a question we can get on a quiz or a test. Yep. Yep. You should be using your unrounded answer. What was the unrounded number there? Was it? I only have the rounded number written down on my sheet here. It does say, but you're right, Brody. You should be using the unrounded number. So whatever it was, 4.79 or 4.812, whatever. Use that unrounded number. In most cases, it's not going to make a difference. But the odd time, that 1 out of 10 time, it will make a difference. And if it's multiple choice, you're probably going to get away with it. But if it's numeric response, then you won't get away with that. So it's a good question, and that's kind of a bad habit to do here. The only reason I did it that way in front of you guys here just now is because I didn't actually, on my answer key, do the electron volts one. So I didn't have the unrounded number to put down. But we should, you're right, put the unrounded number down. OK, we got to look at number 5 now. 5 is the fun one. It says, how does the radius of curvature of an electron compare to the radius of curvature on alpha particle's path moving through the same magnetic field at the same speed? Same magnetic field, same speed. I got a quick question for you first that seems completely unrelated to this one. Let's say I'm 40 years old. Okay, there's only so long that I can use this analogy because at some point it's going to be just not believable anymore. But let's say that I'm 40 years old. Let's say that you're 16. Some of you guys are 16. Okay, let's compare my age to your age. Okay, what's the best way of doing that? Well, we could say I'm 40, you're 16. That's one way to compare them. Just list them. We could say that I'm 24 years older than you. That's another way to compare them. What's the third way to compare them? I'm 2.5 times older than you, right? Right? If you divide 40 by 16, I'm 2.5 times older than you. What's the best way of those three to compare them? The best way to compare them is to say I'm 2.5 times older than you, right? Let's just think of it this way. Okay, let's say that you have a younger brother. You have a younger brother who's 1 year old. You have a younger sister who's 2.5 years old. Okay. When we subtract them, we get 1.5, right? 1.5 doesn't sound like a big number. When we divide them, we get 2.5. So the 2.5-year-old is 2.5 times older than the 1-year-old, or 1.5 years older. Does that make sense? Well, why does it make more sense to divide them and say it's 2.5 times older? Because right now, when they're 2.5 and 1 years old, a year and a half makes a big difference. Right? The 1-year-old can't walk, can't talk, can't do anything. The 2.5-year-old can walk and talk and run around and might be toilet trained and whatever. Right? So there's a big difference in 1.5 years. When they're 20 and 21.5, a year and a half doesn't make any difference at all, right? So to say that they're a year and a half different is not a good way to compare them, because when they're 1 and 2.5, it's a huge difference. When they're 20 and 21, it's no difference. The best way to compare them is to divide them. Okay, when they're 1 and 2.5, we divide them, and we get a ratio of 2.5 to 1. It's a big difference. When they're 21 and 20, we get a ratio of 1.0 whatever to 1, basically showing no difference, right? The best way to compare two things is not to subtract, but to divide. I'm 2.5 times your age. That's the best way to compare our age, is to divide them. Okay? So the best way to compare two numbers like radius of curvature of paths of charged particles is also to divide them. We're not going to subtract these. We're going to divide them. We want to find the radius of curvature of the electron's path compared to the radius of curvature of the alpha particle's path. So let's divide them. Now, if we have the number for both of those, this is easy, but unfortunately we don't. So we have to come up with an expression. We know that Fc is equal to Fm, or mv squared over r equals qvb, or r ends up being equal to mv over qb if I rearrange it. Let's take that value, or that expression, and plug it in for both of these. Let's say mv over qb. But let's make it me ve qe ve over m alpha v alpha over q alpha times magnetic field experienced by the alpha particle. So far, so good? Instead of putting in the numbers, we're just putting in the expressions for the radius of each particle's path. Now, the question tells us that it's the same magnetic field and the same speed. So if it's the same speed, we can cancel out the speeds. Same magnetic field, we can cancel out the magnetic fields. Only because they're the same values. The mass isn't the same. The charge isn't the same. But we can plug in the value for the mass of the electron and the charge of the electron. And then divide it by the mass of the alpha divided by the charge of the alpha. Let's see what we get. I'm going to do this on my calculator because I just noticed that my photocopy of my answer key got cut off at the bottom, so I can't actually see what the number is. Let's pull out the calculator and do this here. Let's say that the mass of the electron is 9.11 times 10 to the minus 31 divided by, oops, got to put a decimal point in there. 9.11 times 10 to the minus 31 divided by the charge of the electron, 1.6 times 10 to the minus 19. Let's press equals. Now let's divide that by, use some brackets here, the mass of the alpha particle, 6.65 times 10 to the minus 27, divided by 3.2 times 10 to the minus 19. We get a number that is 2.7 times 10 to the minus 14. What does that mean? Well, if we divided my age by your age, we'd get a number that would be 2.5. So we'd say the ratio is 2.5 to 1, or I'm 2.5 times older than you. What's the ratio here of the electron's path to the alpha particle's path? 2.7 times 10 to the negative 14 to 1. So in other words, the alpha particle's path has a bigger radius, quite a bit bigger radius than the electron's path. Anybody tell me why? Why would the alpha particle have a much bigger radius than the electron's path, despite the fact that they're moving through the same magnetic field at the same speed? What's the big reason for that? Braden? The mass, yes. The alpha particle is a lot heavier. Mass is related to that quantity in physics 20 that we defined as inertia. If it has more inertia, it's harder to stop it, right? It's harder to change its motion. So instead of going in a tight circle, it goes in a much bigger circle because it wants to go in a straight line. So it's closer to being in a straight line. It's kind of a tough question. But in the end, remember this. If you're ever asked to compare two things, if you're ever asked to find a ratio of two things, if you're ever asked to do anything like that, think divide. There's certain things that we've done this year, right, that we always do the same thing. See that F versus T graph? Area equals impulse. Okay, you see a charged particle speeding up, we think car going down a hill, EI equals ZF. We see the word compare, or we see the word ratio, then we're going to think one word, divide. All right? And if we have two numbers, then great, it's easy. If we don't have two numbers, then put in expressions and see what happens. All right, you also had some more homework on page 601. It was questions 3 to 6a and 7 to 10. Any issues with those questions? 3 to 10 except for 6b. 5 to 6? 5 and 7. Okay, yeah. 3 and 4. So we got 3, 4, 5, 7. 3, 4, 5, 7. 8. 3, 4, 5, 7, 8. Going once, going twice. Okay. 3, 4, 5, 7, 8. We can do that. An electron and a proton, both with the same perpendicular velocity, enter a region with a uniform external magnetic field. What can you say about the deflections of both particles? There's two things that I can think of that we can say about the deflection of these particles. Two differences. One similarity. They both go in circles, right? We know that they both go in circles. That's the similarity. There's two differences that I can think of. What's one of them? without doing any calculations, we know that the proton is heavier, therefore the radius will be larger. It's going to be closer to a straight line than the electron, right? So the radius of the proton's path will be larger, given the same speed and the same magnetic field. Now, if you're changing the speed in the magnetic field, all bets are off, right? The mass isn't necessarily going to make it a bigger radius. But if those things are equal, mass will always make it a bigger radius. What else can we say about them? Besides the mass, what's the difference between an electron and a proton? They're opposite charge, so what's going to happen? They're going to deflect in opposite directions, right? One's going to deflect up, one's going to deflect down. Okay, let's take a look at number 4 here now. Describe the key differences in how magnetic and electric fields affect a moving charge. Let's take that question a step further. Let's delete the word moving. Let's say describe the key differences in how magnetic and electric fields affect charged particle. What if we have a stationary charged particle? How does an electric field affect it? Well, we know that a positive particle experiences a force, which way? With the field. A negative particle experiences a force against the field, right? What about a magnetic field, a stationary charge? A positive experiences, if it's a stationary charge, how's the magnetic force on that particle? I'll give you a little hint. I'm going to write down the equation that describes the magnetic force on a charged particle, right? If the particle is stationary, what's the force on that particle, the magnetic force that is on that particle? Jesse? 0. So a stationary particle experiences an electric force either with the field or against the field. A stationary particle experiences no magnetic force, regardless of whether it's positive or negative. What if it's moving? A positive particle still experiences an electric force with the field. A negative particle still experiences a force against the field. In both cases, they're parallel to the field. A magnetic force on a moving charge is not parallel to the field, but rather it's perpendicular to the field. 90 degrees, right? We have to find that direction by the hand rule. And the palm, of course, is always 90 degrees to the way the fingers are pointing. So there's the answer to that question. In an electric field, charged particles experience a force parallel to the field, either with it or against it. And charged particles in a magnetic field experience a force perpendicular to the field. Five. A positively charged lithium ion is traveling horizontally along the Earth's surface. Describe the deflection due to the magnetic force if the ion travels south to north. Okay, so we're going to assume when they say south to north that they're talking about the traditional way of describing it. South to north would be towards geographic North Pole, okay, or magnetic South Pole. So we've got a particle going that way towards Santa Claus's house. We've got a magnetic field pointing that way towards Santa Claus's house. What's the force on it? 0, because when they're parallel, there is no force, right? What about east to west? That's west. You can see the mountains over there. Okay, that's east. We've got a magnetic field pointing that way towards Santa Claus's house. We're talking about a positively charged particle. Use the right hand. Thumb in the direction of the particle, which is east to west. It's that way towards the mountains. The magnetic field is towards magnetic south or geographic north. Palm points down towards the ground. So the answer for that one would be down towards the ground. Finally, the magnetic field, again, is pointing towards magnetic south or towards where Santa Claus lives. The particle is going upward into the atmosphere this way, thumb upward, fingers towards Santa Claus's house, palm points toward the west. toward the mountains. Now, we can see the mountains in this room right now because we can look outside the window. We know which way is north. We know which way is west because of those mountains. If this is a completely enclosed room, like it will be when you write the diploma exam, how do you know which way is north, south, east, west? Make it up. Doesn't matter. Make it up. Whatever way you're looking, call it north. And then behind you would be south. To your left would be west, and to your right would be east. Doesn't matter. Okay, as long as you're consistent with that frame of reference. Seven. A 0.020 gram metal ball. Haven't seen that in a while. With a charge of -3 microcoulombs is thrown horizontally along the Earth's equator. How fast must the ball be thrown so that it maintains the same height during its motion tangential to the Earth's surface if the magnitude of the Earth's magnetic field is 5 times 10 to the negative 5 Tesla? There's a key word in here, or key phrase in here. What is it? What is it? Horizontal, okay. Okay, not quite as key as the one that I'm thinking of. Abby, is your hand up? No? Sorry? Earth? That's pretty relevant, yes. But there's one four-word phrase, I'm sorry, that really jumps out at me as being incredibly important here. Brody? Yeah. What does that tell us if it's maintaining the same height? It's like being suspended, where we set the force of gravity equal to some other force. In this case, it would be the magnetic force because we're talking about the magnetic field, right? So Fg would be equal to Fm. Mg would be equal to QVB. What are we looking for here? How fast it must be moving. So we're looking for V. It becomes Mg over Q times B. We've got all this now, so we just plug our numbers in. And we solve that, right? I'm not sure what we actually get there. Does anybody have the answer? 1.3 times 10 to the 6. Why do I think Maureen has the right answer there, even without doing the math myself? 10 to the 6. Yeah, that's pretty typical. Could be wrong. You know, she could have punched a number into a calculator wrong and gotten an answer that was really close, but odds are she's right. Pardon me? Did you? How'd you do it? Okay, but you used A as 9.81. Yep. Yep. Okay. Okay. So you really did the same thing. You just did it in 2 steps. Maureen said F is equal to M times A, and she used A as 9.81, right? She said negative 9.81, but whatever. So that gave her the force of gravity. And then she said Q is equal to F over, V is equal to F over QB. And then you plug that value for force in here. So basically, we set them equal to each other at the beginning. You set them equal to each other later on. Same thing. Doesn't matter to me which way you do it. Both ways are good. Final number 8. This one says an alpha particle with a charge of 2 times 1.6 times 10 to the minus 19. We know that anyways, right? We don't need to be told the charge there. Traveling perpendicularly through a magnetic field at a speed of 1.2 times 10 to the negative 5 meters per second. That's a pretty slow speed. But it's possible, right? It's not greater than 3 times 10 to the 8. It's possible. What minimum gravitational force is required to suspend the alpha particle at the same position above the Earth's surface? It's the key word here, one word. Suspend. Right? If it's suspend, we do the same thing as Brody did in the last question. Fg is equal to some other force. What force are we looking for here? Electric force, magnetic force. We're talking about a magnetic field. It's probably going to be magnetic force. I'm sorry? It's 10 to the negative 5. Yeah. Yeah. Yeah, it is. You're right. Now, yeah, you actually don't need the value of mg here because we're looking for the gravitational force. So we can just say, look, Fg equals Fm, and Fg equals QVB. We don't need to plug in m times g. Look, we've got Q, we've got V, we've got B. Solve for it. We get the magnetic force, and of course the gravitational force has to be equal to that. Does anybody have a value for that?